In this lecture, we'll see a summary of the entire Fourier analysis concepts that we studied so far. First, we started out with a motivation for this Fourier analysis. We said that convolution is the property through which we will know what the output of any LTI system is, because the output of any LTI system is the convolution of the input and its impulse response. Convolution is probably a complicated operation when done in the time domain. So we wanted to simplify this. And the thing that we noted first was that phasors, which are complex sinusoids, are eigenfunctions of the convolution operation, which means when we feed in a phasor to an LTI system, the output is the same phasor but scaled with some number. So this is the eigenfunction. And another interesting property is these phasors are not only just simply eigenfunctions but also orthogonal and bounded, and we have infinitely many of them. Just by changing the frequency, we'll get a different phasor. Now we use this property to represent any arbitrary signal as sum of different phasors. Okay, and the thing that we noted in this representation is that you can represent that in terms of phasors, but the power or energy does not change. So the power of the signal in the original time domain representation versus the representation through phasors should have the same power or energy. That's what we refer to as Parseval's theorem. We also saw an analogy through vectors, two-dimensional vectors. So now what should be the choice of this phasors? Now we had two different choices. The first choice was a discrete set of phasors which are basically nothing but harmonics. So we chose a fundamental frequency omega naught, and then we picked up all phasors whose frequencies are integral multiples of that. Okay, so such set of phasors are what we used for Fourier series decomposition. So if we decompose a periodic signal in terms of the harmonics of a fundamental frequency, then that decomposition is what we refer to as Fourier series, and that was possible only for periodic signals. When we showed that this is true, you take the periodic signal whose fundamental frequency is omega naught, then you can expand that or decompose that in terms of a Fourier series representation using only phasors of harmonic frequencies. Okay, and the coefficients of these Fourier series can be obtained simply by projecting the phasor of a particular frequency onto the original signal x of t. That's all. All you needed was the set of phasors and a projection operation that was sufficient to do this decomposition. Now we extended this to any aperiodic signal by taking a continuum of frequencies from minus infinity to plus infinity. In other words, we just had a set of frequency omega, and this omega itself was running from minus infinity to plus infinity, okay, and it belonged to a continuum. So if we picked up this, then we obtained what was the Fourier transform. So we can expand or decompose any signal x of t, even if it is aperiodic or even periodic, through this Fourier transform where we have a continuum of frequencies. Okay, if it is a periodic signal, we'll have to use Dirac delta functions to represent it. Otherwise, we can use the regular Fourier transform without any Dirac delta for aperiodic signals. So you can represent them using a continuum of frequencies, and the projection operation turns out to be simply the same without the normalization. So the Fourier series and Fourier transform are given by these expressions. So in Fourier series, what we have is the periodic signal is just decomposed in terms of phasors, and you just have a coefficient multiplied with each of those phasors. You just scale and add these phasors, that is all. And how to find these coefficients? Just simply project them in one period and just find this projection by normalizing with the energy of the phasor in one period. So essentially this is like the inverse Fourier series, and this is like the Fourier series equation. So you just compute the Fourier series coefficient through this projection, and from the projection you rewrite or decompose the actual time domain signal in terms of the phasors. Going by the same analogy, you can decompose the time domain signal in terms of continuum of phasors in Fourier transform, and the coefficient is given by the spectrum, which is the Fourier transform of the signal, and you just add them up using this integration. So this is what is referred to as inverse Fourier transform, and the Fourier transform gives these coefficients x of j omega, which are basically nothing but projection of this phasor onto the original signal. Okay, and in both the cases, Parseval's theorem is still true. So in the case of periodic signal, we know that all periodic signals are power signals, so it doesn't really make sense to talk about the energy. The power is nothing but the average energy in one period, and that satisfies our Parseval's theorem, which is just the summation of all squared values of the Fourier series coefficients. And for an aperiodic signal, if it is an energy signal, you can just compute the energy in time domain. It will be equal to the energy that you compute in the Fourier domain, of course, with this normalization factor applied. So sometimes it might be easier to compute this integral versus this integral. So whichever is easier, you can use that integral to compute the energy. So the existence of the Fourier transform and Fourier series was given by the Dirichlet conditions. The Dirichlet conditions had three conditions. The first condition said that the signal should be absolutely integrable in a given period, and for Fourier transform it should be absolutely integrable overall. And the second condition stated that there should be a finite number of maxima and minima for a given finite interval. And the third condition said that there should be a finite number of discontinuities in a given finite interval. As long as these conditions are satisfied, for sure the Fourier transform and Fourier series would exist. But if they are not satisfied, then the Fourier transform and Fourier series may not exist. So these are only sufficient conditions but not necessary. So this also led us to the understanding of Gibbs phenomena. Whenever there is a discontinuity, which means there is a very fast change in the signal's value, which means there are infinitely many frequency components that are required to represent that particular point. So there is a discontinuity, right? So because of this, infinitely many frequencies are required. So when you add only finite number of frequencies, you would observe what is known as Gibbs phenomena. This occurs at discontinuities. And also we saw what is the uncertainty principle. So whenever we have a signal which is finite in the time, so basically there is an interval in time, and if the signal is non-zero only in that interval, such signals will always have infinite bandwidth. And if a signal is band limited, meaning it is finite in bandwidth in the spectrum, then it will always extend to minus infinity to plus infinity in the time domain. So this is what we refer to as uncertainty principle. You cannot contain a signal in both time domain and frequency domain. If it is finite in one, it will become infinite in the other. And from this analysis, we substituted those properties for LTI systems, and we found out the existence of frequency responses for LTI systems, which are basically nothing but the eigenvalues corresponding to a particular phasor. What is a phasor? This is e power j omega t, which are the basis of expansion of Fourier series and Fourier transform. So for a particular phasor, the eigenvalue corresponding to the phasor of the LTI system is what we refer to as the frequency response. And this also turned out to be the ratio of the Fourier transform of the output to the Fourier transform of the input for any LTI system. Okay. So this is what we refer to as the frequency response, which is also nothing but the Fourier transform of the impulse response of the system. And we saw the duality property which existed for Fourier transforms, which said that if you know the Fourier transform of the signal, then you can find out the Fourier transform of the time domain equivalent of the spectrum, which will be a time reversed and scaled version of the original signal itself. So this duality property helps us in computing the Fourier transform and an inverse Fourier transform of several signals, which would be otherwise difficult to compute through this integration. And the other important property that we saw was the relationship between symmetry and real and imaginary components. So if we had a real component in the time domain, it would correspond to the conjugate symmetric component of the spectrum, and the imaginary component would correspond to the conjugate asymmetric part, and vice versa for both the time domain and the spectral. So this is very, very important and comes in handy in several different scenarios. And another important property is what happens to convolution in the frequency domain. So anything that is multiplied in the time domain, it gets represented as just convolution in the frequency domain, and anything that is convolved in the time domain is just simply multiplication in the frequency domain. So this is true for Fourier transform. And for Fourier series, anything that you multiply in the time domain, the coefficients just get convolved. And if you convolve in the time domain, then we don't have and relationship for the Fourier series, but there is also an equivalent relationship. However, the kind of convolution that is required is different, which is known as periodic convolution, which we did not talk about in this course, so I'll not mention that here. However, we talk about only the regular or the linear convolution, and if you just linearly convolve any two signals, there is no relationship here for the Fourier series coefficient. And we saw about all different properties in the time domain versus the frequency transform or the frequency series representation. And when we subject the time domain signal to, let's say, conjugation or time reversal or time shift, there is a corresponding change in its Fourier series coefficients or its Fourier transform. We saw what happens. It is very similar for all these three cases. Whenever there is a conjugation or a time reversal or a time shift, we have the same thing happening both in the Fourier series and the Fourier transform. Of course, bandwidth remains the same. But one interesting thing that adds up in the case of Fourier transform is you can do a frequency shift. You can shift the frequency spectrum by an arbitrary value. There is a corresponding change in the time domain signal, which is nothing but a phase change. Okay. And we also saw what happens to time scaling. There is a spectral scaling happening both in the Fourier series and the Fourier transform domain. And we saw the effect of differentiation and integration. So differentiation behaves like a high pass filter, and it just multiplies j omega with the given spectrum, both in the Fourier coefficient and the Fourier transform. And the integration divides by j omega both in the Fourier series and the Fourier transform, but in Fourier transform we get an additional impulse term. This is because the Fourier transform of the unit impulse function, as there is a discontinuity that is present, behaves like this, where we have a Dirac delta coming into picture when we compute the Fourier transform. And we also saw a relationship between the inverse Fourier transform of the derivative of the spectrum. So in the case of Fourier series, we cannot do a derivative or an integration in the spectral domain because they are all discrete signals, they are not continuous. But because the Fourier transform is over a continuum of frequencies, we can differentiate or integrate in the spectral domain, and for that reason we have this property which is not present for Fourier series, which tells us that the inverse Fourier transform of a derivative or an integration of the spectrum is nothing but the scaled value of the original time domain signal. This is a very important property which we use to solve ordinary differential equations and partial fraction techniques, which helps us to solve any circuit analysis problem. The only thing that we need to keep in mind is the inverse Fourier transform of this particular fraction. Once you know this, you can solve any RC analysis problem, any circuit analysis problem by solving the circuit in the frequency domain, not in the time domain, but in the frequency domain.